Welcome to the Explainer. Today, we're taking on what I like to call a calculus boss fight, unlocking the chain rule. We're going to reverse engineer a deeply nested, frankly intimidating math problem to see exactly how its underlying mechanics tick. Let's dive right in and decode this thing. So, how exactly do we tackle a deeply nested mathematical puzzle? Well, think about composite functions. They're essentially layers upon layers of equations. It's kind of like a beautifully engineered set of mechanical gears, or, a classic set of Russian nesting dolls. You can't truly understand how that tiny innermost doll was carved just by staring at the giant outer shell, right? You've got to take them apart piece by piece. And that's all the chain rule really is. It's our trusty instruction manual for safely unstacking those layers to see how the whole shebang fits together. Okay, let's dive into this. Right at the top, inside that red box is our ultimate goal. This is the boss fight I was talking about. We need to derive e to the power of x minus 1, all squared. Now, because we've got an exponential function, a squared term, and a polynomial all interacting at the exact same time, we absolutely need a solid strategy. Trying to solve this whole thing in one massive leap? Yeah, that's just not going to work. We have to deconstruct it. Enter lemma 1. This first step beautifully breaks down our massive problem into 3 bite-sized, manageable layers. First up, we grab the innermost layer. U equals x minus 1, which gives us a simple derivative of 1. Okay, easy enough. Next, the middle layer, v equals u squared, giving us a derivative of 2u. And finally, we hit the outermost layer, y equals e to the power of v, which just derives right back to e to the v. See what we did there? By isolating the layers, we literally just turned one terrifyingly complex derivation into 3 super elementary ones. But, all right, here's the catch. We have these nicely isolated derivatives now, but how on earth do we mathematically link them back together? Before we can solve the puzzle, we have to step back for a second to lemma 2. We need to actually build the theoretical machine that measures change across all these different moving parts. We have to establish exactly how points on a curve relate to one another before we can accurately wire our separate variables back together. To build this machine, we really have to look at the difference between average and instantaneous change. Now, we all know calculus is absolutely obsessed with the instantaneous. It's like looking at the exact speed on your car speedometer frozen in a single split second. But to get there, we actually have to use the secant line, which just measures average change over a set distance. That average change is our crucial starting block to link the variables before we can even think about deriving the tangent line. So to make that jump from average to instantaneous, the author uses this fantastic physical narrative. Quote, suppose the point P1 moves too close towards P0, such that the vector approaches 0. End quote. I love this because you can literally visualize it. Imagine those 2 distinct points of our secant line sliding closer and closer and closer together along the curve. The distance between them shrinks until they're basically sitting right on top of each other. That sliding motion, that is the absolute key to unlocking instantaneous change. Now, lemma 3 is where we translate that physical sliding action into hard math. If you look closely at the equations here, they're expressing the change, let's say delta y, using the initial derivative. But, and this is important, they add this tiny little error gap represented by the Greek letter epsilon. That epsilon is there because while our 2 points haven't perfectly merged yet, it's basically a mathematical buffer that's keeping us from getting a perfectly exact instantaneous reading. So, the million-dollar question is, how do we get rid of that annoying little error? Well, welcome to the engine room of calculus, folks. We apply limits. Limits are the essential mechanism we use to completely crush those error japs. By pushing our limit closer and closer to 0, we force the distance between our 2 points to shrink until that epsilon error term just ceases to exist. We literally move from just approximating things to finding the exact absolute rate of change at one single point. Just follow the cascading limits here for delta x, delta u, and delta v. It is so satisfying to watch. As the distance, the delta, approaches 0, watch what happens. As delta x goes to 0, bam, that epsilon u term completely vanishes. As delta u goes to 0, the epsilon v term vanishes. The error drops away entirely. And what are we left with? Incredibly clean, pure differential equations for du, dv, and dy. It's mathematical magic. By clearing away all that noise, our chain rule machine is officially forged. By substituting those clean limit equations back into one another, everything connects sequentially. Think about it. dy relies on dv, dv relies on du, and du relies on dx. When you substitute them, the variables link perfectly together, forming one unbroken chain. This right here gives us the official chain rule formula. The derivative of y with respect to x equals the derivative of y with respect to v times the derivative of v with respect to u times the derivative of u with respect to x. Now, what's really interesting here is how it all comes together in this final step. With our theoretical machine built and our formula forged, it's time to run the components. We take those original bite-sized layers we figured out way back in Lemma 1 and we feed them straight into this newly built chain rule formula. We are finally ready to beat the boss. And here is the final resolution. We take our individual derivatives, e to the power of v, 2u, and 1, and we simply multiply them all together. Now, to translate it back into our original language of x, we just substitute v and u back into the equation. Once you expand that out, it yields this incredibly clean, elegant final answer. 2x times e to the power of x minus 1 squared minus 2 times e to the power of x minus 1 squared. Boom, the system is fully decoded. We started with an equation that looked deeply, almost aggressively complex. But by breaking it down into individual layers, understanding the theoretical connections between them, and then chaining them back together, we found the solution with perfect logic. So here's what I want you to think about. How does this underlying methodology of breaking complex problems into smaller, perfectly connected chain links apply to fields far beyond calculus? Whether you're reverse engineering a piece of software, analyzing a global supply chain, or even trying to understand a complex biological system, couldn't this exact same logic be a total game changer? Take a look around. What complex systems in your own life might just be a few simple layers waiting to be deconstructed? Thanks for joining me on this explainer, and keep questioning the systems around you.